Please help me welcome Professor Philippe Schwaller, who will be talking about teaching language models to speak chemistry from design to synthesis. Thank you.
Thanks so much for the invitation. It's a great pleasure to be here today and kind of give this virtual talk. So yeah, as you all know, in chemistry and material science, we have kind of a nearly endless space to explore. If we take drug-like molecules as an example, then the estimated number is 10 to the power of 60. In my lab, we're kind of thinking about different approaches, how we can accelerate this materials or chemical design cycle using machine learning. From what kind of molecular material do we want to make? Always thinking of experimental validation. We're purely digital lab, so we're covering that mostly with collaborations. And yeah, the reason why this is not really done is that typically like the machine learning part is ready after, I don't know, 6 months, but experimental validation takes a lot longer because it's actually quite hard to make materials and molecules. And that's why we're also kind of focusing, at least a part of the group, on synthesis planning and optimization. Today, I will be focusing on like kind of small language models for sample efficient de novo design, and then go all the way to large language models agents for chemical research. But at the kind of foundation of all that is the foundation of using kind of language models in chemistry are text-based representations. And what is kind of super impressive is that this mice representation, which was introduced back in the 80s, and where you see an example on this side where you can kind of follow the molecular graph and use the carbon, nitrogen, carbon, then the branching and the ring opening by the numbers, is still used today. And what I kind of developed during my time in Cambridge, were also working with IBM Research, was the first transform model that was applied to chemical tasks. And back then it was still an encoder decoder architecture, and we used it for chemical reaction prediction, where we would translate from not one language to another language like it was originally introduced, but from like kind of precursor space into the most likely product space. But using such representations, we can kind of make use of methods that were developed for human languages and apply them more or less one-to-one to tasks in chemistry. And I will start with focusing more on the design of molecules with desired properties. And there, like one typical approach is to use distribution learning. Like, okay, at the start of any approach, typically you take a large database of molecules or materials and you pre-train a model so it can at least produce some grammatically correct molecules or materials. And then if you have a few labels available, what you can do is kind of to do a fine tuning on those measured molecules and kind of sample from this fine tuned model to have like molecules that are in a similar space. But often you want to design something where you kind of know the desired properties, but you have, yeah, you want to have true discovery, and you don't know any like molecule material that has this specific property profile. And that's where goal-directed learning comes in, and where you would start with the pre-trained model, sample a few examples, candidates from it, then score those designs, and then based on that, update the model and run several iterations like that. I think that the biggest challenge in that is to have a scoring function that kind of maps with the experimental outcome that you would desire. What my group is currently interested in is to push the boundaries of those de novo design methods and to make them as sample efficient as possible. if we define like one measurement, one kind of one computational prediction or simulation, or even an experiment as one oracle call, then sample efficiency is how few oracle calls do we need to get molecules that that are above a specific threshold in the properties that we are interested in. And we could do that with machine learning models that are very, very cheap, maybe a few milliseconds to kind of get prediction. But the problem with them is that they typically work very well in distribution, but when you want to discover a molecule with kind of a property profile you didn't have in your training data, then they're usually really bad at predicting out of distribution and kind of useless for that task. Then you could kind of in drug discovery use molecular docking or semi-empirical methods in materials design, or you could like take computationally more expensive methods and kind of have higher accuracy predictions and labels. And if we have sample efficient generators, then suddenly like those more expensive methods become accessible in a de novo molecule design loop. And tackling that, we developed two different frameworks, like augmented memory, which was strongly based on reinvent from AstraZeneca, and then we decoupled it with Saturn and updated the models and so on. But what I want you to quickly show is that there are plenty of de novo molecule generation benchmarks. This one, the PMO, the Practical Molecular Optimization Benchmark from Connor Colley, it was published at NeurIPS 2022, and they're like the special thing they've kind of put inside that benchmark is that the number of oracle calls is limited to 10,000, which is kind of still a lot, but at least like kind of constrains the models. You cannot train your model with like 2 million oracle calls, which is feasible if it's only like a similarity measure, but becomes infeasible if it's a simulation. And the kind of surprising thing is that on that benchmark, at least when we published augmented memory, like the two best performing methods were reinvent, which is LSTM based, so very small traditional language model, and augmented memory, where we included some more tricks to kind of like optimally use all the labeled data that we had. In Saturn, which we released also on archive and is currently under review, we managed to like kind of change the language model to be even more sample efficient. Like in plenty of the cases that you have in the field, it's like kind of people went from LSTMs to transformers, got a lot of improvements, and then stayed with transformers. Here in that case, somehow, like we tried transformers several times, and we couldn't really see a large benefit over the LSTM models. But more recently, like state space models were introduced, which are kind of somewhere in between recurrent neural networks and transformers, try to kind of combine the best of the two worlds. And based on that, we could see some interesting behaviors on kind of, I would say, rather challenging multi-objective optimization tasks with kind of an oracle call limit of 1,000. What we see is that the yield, like kind of the number of molecules that we generate that are above a specific threshold increases. The oracle burden, like how many oracle calls we need until we find the first like interesting molecule, is decreasing, and it gives us some hope that like within like 100 simulations, we are like kind of we would be able to with 100 labels, we would be able to find interesting molecules depending on the task. Another cool thing that we found in that work is that, well, like more traditional methods would always like kind of explore more or less the globally the space. We found this hop and locally explore behavior with the Mamba-based models, where initially it would kind of explore, but then like after a few rounds, it would kind of like always take a step towards like higher, better molecules and kind of here you have, if you want, this same behavior like visualized a bit differently. You have this global exploration kind of phase, which is almost or the whole like 1000 calls in or like the 10 epochs and in the RNN phase. And on the other side, you have kind of you move much faster into a local exploration than taking a step into another kind of space with interesting molecules, locally exploring it there. This is like kind of measured at the end of every epoch, like when you're scoring a batch of molecules. What can we do with that? Like, for example, this is work by Serena that this is still unpublished, but kind of presented at different workshops. And this is for the Morita-Baylis-Hellman reaction, which is typically like catalyzed with organocatalysts. And for that specific reaction, like the Janssen group in Denmark has published a scoring function where they kind of compare the energy of like the reactants and the transition state of the rate limiting step, and based on that, like score the different catalysts. And they were able to even experimentally validate the suggestion. And taking this scoring function, we could show that with a fraction of the budget, we could find as interesting molecules with Saturn. I think what excites me the most here is that there's like ongoing discussion whether we can use 2D SMILES generator to design in 3D, and this is actually like one super nice showcase. This is one of the best or the best design catalyst in kind of one of the runs, and you see in 2D, and here you have kind of the transition state, and somehow just by having this 3D reward, like just a number based on how well kind of how well basically like the design catalyst would stabilize the transition state, the model within like this Oracle call budget of 1000 was able to come up with structures that are bifunctional, that contain this urea motif that stabilizes the transition state, a rigidified linker that matches exactly the kind of length that you need to kind of have the functional groups placed at the correct position. So I think the going like designing in 3D with a 2D generator is kind of cool. What else can we do when we have like kind of better or more sample efficient models? For example, in plenty of the cases, like synthesizability is kind of the bottleneck. And there were some works in the recent years that kind of try to incorporate constrain like the generation with the synthesizability and with some synthesizability metrics, or like kind of to like use reactions to put together molecules and stuff like that. And we thought, why not directly those models typically in the end evaluated whether the generated molecules can be like retrosynthesized with a tool like AstraZeneca SynFinder. And we thought, like, if we have sample efficient models, we could potentially even kind of like optimize towards the final retrosynthesis tool. And this kind of worked. And then we pushed it one step further, and we said, but now what would be even more exciting is if we could actually constrain like to a set of building blocks that we want to see in those syntheses. So like now you optimize for properties on one hand, plus you're kind of you want to find a synthesis route, but not any synthesis route, a synthesis route that contains some of the some of the enforced building blocks that you want to have. And this could be like useful for upgrading, like for to design molecules from starting from bio-based building blocks, or improving hits, or like starting from building blocks that are available in a lab. And if you imagine that, this is suddenly a really kind of sparse reward function, because there's kind of only a few molecules that exist that really satisfy that. So we had to come up with a reward function that would kind of convert that sparse reward into a dense reward. And our solution to that was this Tanimoto group overlap that combines Tanimoto similarity with a substructure match. And you have the equation down there. But let me just show you like kind of what we can do with that. We can kind of say, hey, uh, this is a set of enforced building blocks, or those are bigger molecules that we want to start from. And given that set and the reward function, we can kind of start finding molecules that have a route that contain those specific building blocks somewhere along the route. If you're interested in a recent review on that topic and you want to learn more, I think like this one, I can just highlight that one. I think what is exciting there is that we really made the effort to go through all the literature and also see whether we had like which like studies were actually experimentally validated, and kind of extracted a lot of information on them. And even after the review, Jeff continued to collect all the studies that he found on this GitHub repo. You already like heard that synthesizability is always kind of an issue, and if we focus more on the make part and chemical synthesis, then there were some like trends in the last few years, like in 2017, 18, you have like the first kind of language models for on chemical reactions, mostly focusing on a single modality for reaction prediction, converting like reactants into a product, retrosynthesis or condition prediction. Then there was kind of a phase of like, hey, why don't we try to combine multiple modalities? Like, can we convert chemical reactions into structured actions that can, for example, be run by a robot? And more recently, with like GPT and yeah, those very large and general language models, we've seen a shift towards like trying to incorporate some chemistry into those general large language models. And with Kevin Jablonka, we worked on fine-tuning those large language models. And another way to make them useful is to augment them with chemical tools. And there are like this the work I will present in the next few slides, but there are also plenty of other examples from Alana Spurguzik or Gabe Gomez in the US. Yes. Back when we first worked on that, like it was even pre-GPT-4, but like the previous models were even worse at chemistry. So kind of like yeah, it's not a strength of those models, but what we had available are excellent chemistry tools that all lived somewhere with different APIs, GitHub repos, and so on, all a bit in isolation. So our idea was kind of to build one agent that could use those tools to do something useful, and we called it ChemCrow. And yeah, so what tools did we give to ChemCrow? We gave it some molecular tools, then some general tools to kind of do the typical web and literature search. We gave it reaction-specific tools and also some safety tools. And given that, a user could just prompt it, and instead of like now having the language model just hallucinating something, we forced it to like think about the problem, select an action, basically a tool that would kind of provide additional information, write the input to that tool, and then observe like kind of the get back the results and think about what next step to take. I think what is exciting here is kind of that this is all language based, but again, you could think of having a tool that takes, for example, a smile as an input, goes into 3D, runs a simulation, comes back, and provides kind of some information as an output, again in language. And language is typically the way we communicate chemistry in the end. So yeah, one like short kind of use case that we had was plan and execute the synthesis of an insect repellent, and then the model, the agent went and searched for insect repellents, selected one, DEET, and but kind of this this kind of abbreviation doesn't tell you anything about the structure, so it used another tool to convert DEET into the corresponding smiles, which was then compatible with the reaction planning tools that could provide the retrosynthesis together with the actions to execute the different steps. And back then, we connected it to RoboRxN at IBM Research in Zurich, and after 2 hours, we could have the synthesis. Yeah, we observed that we had actually synthesized DEET. This is just a video. I don't know if you hear the sound, but an old video of that platform, which is still kind of running at IBM Research in Zurich. And, yeah, also built on CapSpeed. We had some other use cases more towards thiourea organocatalysts, where we had kind of to provide a bit more information, and it was able to synthesize a few of them. And currently in discussion with some self-driving labs in Switzerland also to continue in that direction. There's an online kind of interface that basically shows you the tools that are available and kind of where you can interact with that model. And yeah, it's modular. You can, I think, like kind of back then it was one of the first demonstrations of such an LLM agent in chemistry. In the meantime, we would kind of build it completely differently, and would not back then really like GPT-4 was the only model that would follow like instructions well enough to complete such tasks. In the meantime, you have plenty of other possibilities, and you have more use cases in the paper. Yeah, one crucial challenge I would say that we always had is kind of how do we benchmark those large language models in chemistry? And I just wanted to highlight some recent work with Kevin Jablonka, led by him at the University of Jena, where we curated a massive data set of questions, and we also let human like kind of try to answer those questions, and then we benchmarked a lot of the closed source and open weight models, and kind of the closed source models are actually performing quite well on those questions that come from plenty of different kind of fields of chemistry. Yes. We also kind of had 19 human experts that kind of like answered a lot of those questions, and they were also allowed to use tools, and we would track that. And you see how using tools, for example, web search or calculator and so on, can help you like solve those questions better. This, yeah, the question is, this is super nice. We can kind of see whether language models on those multiple choice questions are actually good at picking the correct answer. But is this really reflecting what we want to see from language models? So, like, kind of, we it's something we thought a lot about in the lab, and we kind of tried plenty of use cases with large language models. And what we always see more or less is that for property prediction, like in the low data regime and so on, they work reasonably well. They work well for multiple choice questions. You can use them together with tools in agentic workflows. But if you really want to combine natural language and some kind of reaction prediction tasks and so on, they often produce quite a lot of invalid smiles or lack of diversity, and it's kind of yeah, it's a bit it's a bit of a pain, and you can do more or less the same with much smaller models and have a task specific model. So, but what we observed is that if you would give it the structures and the reactions as smiles, the analysis that the language model could perform, like detecting, hey, what is it, what kind of reaction is this? Like, kind of, what's the potential mechanism, how this would happen? They're actually not that bad. So what we thought is like to combine those language models more as kind of chemical reasoning, very flexible chemical reasoning engines with traditional search algorithms, as you see, for example, for retrosynthetic planning. And there we can really think of like saying, hey, look, I'm looking for a route. I really want to kind of disconnect something at a specific place. Like this is the steerable synthesis planning. Okay, I will just have a next meeting starting in 15 minutes. I will dismiss that. Yeah, no, but back to the talk. Like this is thinking of steerable synthesis planning, where you kind of a human expert, like the what we see with retrosynthetic tools is that they can produce a lot of different routes for any given target molecule, but only a few of them really make sense. But if in the top 10 ranked routes, you have 8 that are complete garbage and maybe 2 that make kind of sense but are not exactly what the human expert was looking for, then you have an issue and they will use that tool one time and then give up. But if now you give an expert the possibility to say, hey, please break the pyramid ring in an early stage and get all the other rings from commercially available molecules, then you can actually run this search and let the language model rank the outcoming like routes according to the human query. And like kind of what was not feasible at all like 1 year ago, like with more and more recent models, somehow they really improved in chemistry, and we can actually kind of use those language models like to reason about complete synthesis routes. We went up to like synthesis routes of 26 steps and kind of provide kind of an alignment score with human queries, which is kind of super impressive. And we often measure like kind of the results. Also, we have a total synthesis chemist in the lab, and his excitement is the main score we are optimizing for. And this is something he was very excited excited about. Another thing, like going from this super large scale of like synthesis routes, when we look at single reactions, we have like the reaction mechanisms, you have elementary steps, and at least in some basic reactions, you can kind of we have a sense of what would be the ground truth moves that would happen to turn the reactants into the products. And also there, surprisingly, like kind of more the most recent models like become more and more performant as like selecting the actual understanding like at what stage you are in the mechanism and selecting the correct next elementary step. And we also like played around with like adding some more contextual representation about the specific reactions, but like kind of well, this helps boost a lot like the older and smaller models, like Claude Sonnet 3.7, which was released like a few weeks ago, is actually performing well just by itself. I think like I'm running out of time, so like let me just point you again to augmented memory in Saturn if you're like kind of interested in sample efficient molecular design. And then I think we've showed that like in specific cases, we can really use those LLMs somewhere in combination with chemistry tools to kind of lower the barrier to for access to those tools and like kind of streamline the workflows. With ChemCrow, we had like one of the first demonstrations from prompt to actual synthesis on a robotic platform. Evaluation, as always, is super challenging in those new tasks. And in this recent preprint, we're kind of exploring how LLMs could work as chemical reasoning engines. And yeah, this is the whole team. I don't know why I'm kind of highlighting Salome, but I most likely made a mistake when copying this slide. But like, this is team, the funding. I'm very grateful for that. And yeah, thank you very much for your attention.
Thank you everyone for attending. The next webinar is on the Wednesday, the 23rd of April at the same time. If you have any speaker nominations for ECRs or also main speakers, we're also welcoming this as part of Alchemy. And if you want to connect with us, again, this is a reminder, you can scan the QR code and you can have link to all, you have the links and details here. Thank you for joining us and we'll see you at the next one.